Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Draw the influence lines for the vertical reactions at the supports and the shear and bending moment at point C of the beam shown below is constant. Plot ordinates to the influence lines every 4-meter intervals. Take note, moment of inertia of portion AB is just I, while for portion BD it's 3I. So I will solve this not in more details anymore because I already gave you the idea how to generalize the construction of the influence lines for the different functions, response functions, in terms of the position of the unit load, x1 or x2. This time it's x. So let's specifically solve the required response functions at every position of the unit load to shorten the solution. Take note that when the unit load is over a support, it's only the reaction over that support that will be 1, and the rest of the functions, response functions, will be zeros. So that's the idea. So this is the first position of the load. It actually begins with x is 0 at A. So reaction at A, AY is 1, and the rest will be 0. So that's the idea. So at this position here, writing 3 moment equations on span ABD, and take note that moment at D is 0 because the unit load is still here. And also that moment of inertia of portion BE is 3I. Portion B is 3I. So we have 0 plus 2 MB quantity 8 plus 8 over 1 plus 8 over 3 because the moment of inertia of portion BD is 3. Then plus moment at D, which is 0, plus PA over L, or 6A1A over I1L1 is equal to 1 times 4 over 8 times moment of inertia 1 quantity L square minus A square. So 8 square minus 4 square. Then for portion BD, there is no load, so plus 0 equals 0. Simplifying and solving for MB, MB is equal to negative 1.125 for X equals 4 particularly. So take note, when X is 8, when the unit load is over B, it's only By that is 1. Then MB will be 0. The rest of the response functions required in this problem will be 0. So next position would be when the unit load is at X equals 12 there. So AB will have no load. It's only BD that has a load. Moment at D is still 0. So writing 3 moment equations on spans ABD, making moment at B as the redundant force. So 0 plus 2 MB quantity 8 over 1 plus 8 over 3 plus moment at D0 plus 6A1A over L1 for span AB is 0, while 6 area 2B over L2I2 for span BD is 1 times 4 over 8 times 3, moment of inertia 3, quantity 8 squared minus 4 squared, and it is equal to 0 for supports that are unyielding. Solving for MB, MB is equal to negative 0.375 for X is equal to 12. Then finally, when the position of the unit load is at E, moment at D would be negative 1 times 4 or negative 4. So writing 3 moment equations on ABD again, take note that moment at A0. So 0 plus 2 MB quantity 8 over 1 plus 8 over 3 plus negative 4 times 8 plus 0 plus 0. There are no loads on AB and BD. So equals 0. Solving for MB, MB is equal to 0.5 for x equals 20 in particular. Having found MB, then we draw moment free body diagram for portion AB, and the position of the load is here, unit load, and let's have MB. So considering AB, summation moment B equals 0, we can have AY when the unit load is here. So AY times 8 equals MB, which is negative 1.125 when x is 4, plus 1 times 4. So AY is equal to 0.3594 for x equals 4. Then when x is 12, because when x is 8, AY would be 0. So when x is 12, then there's no unit load here, it's here. So AY times 8 equals MB, and MB when x is 12 is negative 0.375. So AY times 8 equals negative 0.375. So AY equals negative 0.0469 for x equals 12 in particular when the unit load is here. Then when the unit load is at E, at D, AY is 0 again. Then at E, when x is 20, moment at B is 0.5. So the equation considering AB, summation moment B equals 0, is AY times 8 equals 0.5. So AY equals 0.0625 for x equals 20 meters. Then, considering the entire system, summation moment D equals 0. So AY times 16 plus BY times 8 equals 1 times 12. 1 in general, 1 times 16 minus x. The distance of the unit load in general in terms of x is 16 from D. 16 meters minus x. So we can derive By. Generally, By equals 1 over 8 of 16 minus x minus 2ay. This is for all values of x. Then summation forces y equals 0. So that means d sub y equals 1 minus ay minus by. Summation forces y equals 0. Ay plus by plus dy equals 1. So dy equals 1 minus ay minus by. So this is the free body diagram for the portion C to E. Then, and the movement of the unit load is from 0 to 12. So this is the free body diagram when the unit load is now on portion CD, and therefore this distance is x minus 12. So for this free body diagram, let's derive V sub C. V sub C, summation forces y. V sub C plus dy equals 0. So that means V sub C is negative dy for 0 less than equal to x less than 12, excluding 12. Then when x is greater than 12, the unit load is here. So the unit load is now involved. So V sub C is 1 minus dy for x greater than 12. Then for moment, summation moment about C equals 0, m sub C equals dy times 4, or m sub C equals 4 dy for 0 less than equal to x less than equal to 12. So including 12 for moment. Then for x greater than equal to 12, because the unit load is now present in the free body diagram. So m sub C plus 1 times x minus 12 equals dy times 4. So that means m sub C is 4 dy minus 1 times x minus 12 for x greater equal to 12. So from here, all the required response functions are already set up, then we can plot ordinates to the influence lines of these respective response functions. So beginning with MB, although MB is my chosen redundant and not required here, only these 5 functions. So anyway, when x is 0, MB is 0. When x is 4, so MB is negative 0.125. When the unit load is over B, so MB is again 0, just to the left. Or when x is 12, just to the left, MB is negative 0.375 here when x is 12. And also for x, when x is 12, just to the right. When x is 16, when the unit load is over D, MB is 0 again. Then when x is 20, MB is 0.5. AY, which is when x is 0, when the unit load is here, so AY is 1, of course. When x is 4, AY is 0.3594. We already computed that. When the unit load is over B, AY is 0. When x is 12, AY is negative 0.0469 when x is 12. When x is 16, the AY is 0. Then when x is 20, AY is 0.0625, which is this. Then when x is 0 for BY, this is the formula. 16 over 8, 2 minus 2 times 1, 0. When x is 4, 1/8 of 16 minus 4 minus 2 times AY. AY is 0.3594. So that's why BY is 0.7812. When x is 8, BY is 1 because AY is 0. Then 16 minus 8 is 8 over 8 is 1. Then when x is 12, 16 minus 12 is 4. 4 over 8.5. 0.5 minus 2 times AY. And AY is negative 0.0469. That's why BY is 0.5938. When x is 16, with the unit load is over D, BY is 0. When x is 20, then 1 over 8 of 16 minus 20, negative 0.5, minus 2 times AY, minus 2 times 0.0625, so BY is negative 0.6250. Then for DY, this is the expression 1 minus AY minus BY. So 1 minus 0.3594 minus 0.7812, so that's the value of dy when x is 4. Then dy is only 1 when the unit load is over D. The rest, over the support, it is 0. Then when x is 12, so here dy is 1 minus negative 0.0469 minus 0.5938, so 0.4531. Then when x is 20, 1 minus 0.0625 minus negative 0.625 is 1.5625. Then for shear at C, when x is 0, shear at C is 0. When x, this is the formula, negative dy, so negative 0.1406, so positive 0.1406, negative of 0, so 0, negative of, just to the left, negative of 0.4531 is negative 0.5531. Then v sub c, just to the right of c, or when x is greater than 12, 1 minus dy. So 1 minus 0.4539 is 0.5469. Then 16, shear at c is 0. Then at x is 20, 1 minus 1.5625 is negative 0.5625. For MC, This is the formula up to 12. This is the formula for x greater equal to 12. So dy is 0, so 4 times 0 is 0. 4 times negative 0.1406 is negative 0.5624. 4 times 0 is 0. Then 4 times 0.4531 is 1.8124. Same is true here, 12 to the right. Then 4 times dy, 4 times 1, 4, minus 1 times 16 minus 12, so 4 minus 4, so 0, MC. Then here, 4 times 1.5625 minus 1 times 20 minus 12 is negative 1.75. So that's it. Then let's plot this on the next slide. So plotting, we begin with AY. So it begins with 1.35940, then negative 0.0469, 0.0625. So that's the influence line for AY. These are the ordinates. Then for BY, it begins with 0, 0.7812, 1, 0.5938, 0, negative 0.625. So that's the influence line for BY. Next, for dy, it begins with 0, negative 0.1406, 0, 0.4531, then 1, 1.5625. So that's the influence line for dy. Then shear at C begins with 0, 0.1406, 0, negative 0.4531 just to the left, then just to the right of 12.5469, then 0, then negative 0.5625. So that's the influence line for shear at C. And finally, for moment at C, begins with 0, negative 0.5624, 0, 1.8124, 0, negative 1.75. So that's the influence line for moment at C. So that's it for this problem. Because we already have so many examples, then I will not expand the explanation further.